Before the official proceedings get started, I want to make a little announcement. Thanks to Ken Anderson. We're very honored in the CS department to have faculty member named Professor Leisha Palin, a longtime member of the faculty, has just been named a distinguished professor of the university. Woo! For those of you who are not in the know, these are rare awards. One, the second one, but the computer science department is one. And it is the highest honor at the university awards to the faculty on this campus. So we are extremely proud and happy, delighted to have you. Okay, and now on to the topic of the day. It's my honor to welcome Professor Nikolaus Correll to this week's program. Nikolaus did his undergraduate work at ETH in electrical engineering, got his PhD in computer science from EPFL, which both of which are in Switzerland, for those of you not on the acronyms. He came to the United States to do a postdoc at MIT with John Roos before coming here. And so I think make sure I get all this many awards. He holds both a NASA and NSF Career Award, Provost Faculty Achievement Award, the 2022 Open Educator Award. You going to talk about the book?
Yeah.
Okay, so we'll find out about the book. And he's mentored 14 PhDs this time here at SC. So welcome, Nikolaus.
Thanks. Thanks a lot, Jim. So I will talk about mobile manipulation, robotics, and the things that I've done in the last 5 years in that space. And so I want to start with a little overview where we are at in robotics. And what I chose is competitions that really drove the field, because in 2005, DARPA started something they called the Grand Challenge, and it was a car that had to drive through the desert to Las Vegas. And the Stanford team won that with the Volkswagen in 2005. And then 15 years later, we had the first commercial ride from Waymo with no safety driver in 2020. And we also now have companies that deliver food and things like this. And so DARPA got really excited about this idea that basically any problem they have, you can just solve by having these competitions. And they started doing one in mobile manipulation with robots walking around and had to open this fire hose thing and drive a car and things like this. And this was a complete disaster because the robots all flipped over and things like this. And you always see videos like this in our classes. And then they turned it down a little bit and said, okay, let's push that mobility further, and started to do the Subterranean Challenge, which Chris Heckman and Sean Humbert and Eric Fruit won third place, $500,000 this year, which is really great. But manipulation is just too hard right now. And at the same time, the research community has started to organize competitions at conferences, and it always looks like this. There's a bunch of stuff that they think people have at home. And there's ideas like, oh, take the scissors and cut something out, and then they just see what happens. And we've been participating there for the last, from 2016 to 2020. And we also participated at the World Robots Summit, which is an industrial robotics competition, at the Amazon Picking Challenge. And we never won anything, of course. But we did participate and got second place, and it's all completely random, because then I think the last time in Macau, power, when all the people plugged in the robots, power started shaking, the robots turned off, nothing worked anymore. So the competitions is really not the environment to test things. But it didn't really become a commercial success. So Amazon, I think they did this picking challenge a couple of times. And now we have Right Hand Robotics, which is a rather big company, and Kindred, which was sold to Ocado, an English grocer. But I think it's a huge opportunity still, because when you think about it, the whole consumption chain from raw materials, they get made somewhere, then shipped and stored, then shipped again, and then they get consumed, and then they get recycled. And so technically all of these things require a lot of manipulation along the way. And now you can see how you have autonomous ships, obviously, you have autonomous cars, and you have autonomous carts inside the storing facilities or the manufacturing centers. So people are working very hard on automating all of this, but what they cannot do is automate all this manipulation. And so when you look at companies, for 30 years, big companies offer manipulation of that nature. Then of course, in the car industry, people do welding. And now recently you might have seen Boston Dynamics made a big splash unloading trucks with these weird, I don't know. Then you have warehouse robotics. I have only one example. There are hundreds of companies. I am robotics. For consuming, this is a robot that can feed people who have Parkinson or otherwise handicapped. And finally, here in Boulder, it's a CU grad, Mateo Horowitz, who started AMP Robotics. And that is about picking trash out of and recycling. And they raised a lot of money, very successful right now with that company. But all of these are very specific solutions. And what we really want in robotics or in computer science is to have like general manipulation and move away from these purpose-built things. So I can do all of these tasks that you've seen because I have two hands and I have eyes and I'm reasonable skilled to do these things, but robots are still far away. So let me start with a tutorial on manipulation. The problem with manipulation is it looks very obvious, but it's very, very hard. The brain has a lot of its volume is for manipulation. And the big problem is the basic problem is to provide constraints on such a thing at the same time. And when I say constraints, I mean that the screw cannot get away anymore. And if you provide only one constraint, then the screw will slip or fall. And then, once you are ready to provide the second constraint, then it's gone. So it's difficult. And one way to do this is, of course, to increase the accuracy at which you perceive the thing that you want to manipulate. Then you can plan better. And that's how we started out. And we came up with in 2016 with like a tactile sensor. And I think I showed that before, but just a little history. And this is one of those competitions. And now the robot has these fingers that are augmenting that very bad Xbox Kinect that we used at the time, or was an Asus. And so now you can hardly see anything here, but now it goes and thinks where the spoon is, and then it would use the tactile sensors to actually avoid, smacking it, but then can grasp it. And then there were tasks like getting beans out of this and pouring them over, and they got points that way. And so I got really excited, and we started a company to sell these tactile sensors. And I did sell them, but we then, I'll get to that later. So this is how it looks like. We came up with these sensors and made a hand, and then we grasp strawberries. And people always grasp strawberries and raspberries and say it is so difficult because they are so soft and the robots are so metally. And so the idea was to use these sensors to detect the touch event, which it actually does, and also things like this so that you don't squeeze into the strawberry. But the experiment was actually funny because my people then told me that they actually didn't use the sensors, too lazy, because it's too much code and too much work. And the thing is, it actually works without the sensors. And because the reason is you can use compliance. So compliance means I make this thing compliant so that it doesn't keep moving once it hits something, and it stays there, and so then the other finger moves in. And you can do that so gently that you can even pick up the strawberries. And when we realized this, we forgot about the tactile sensor, and we just said, well, the key is, which happened also at the same time, Intel came out with a real good camera that could see very close. And so we built a hand that has the Intel real sense here in the center, has two individual motors that can do torque control. And we got a nice patent, and now Google also has a patent like this, but it's later. But I don't think they care anymore, which is a different story because right now robotics is not the hottest field on the planet. But it's nice because I think this is a very good idea to use this camera in the hand and use these articulated fingers. And so in case you don't believe me, which you shouldn't by default, you can get these strawberries the same way without these sensors by just using motor control so gently that you don't squeeze them. Now, it doesn't prevent people from publishing papers on soft robotics and saying, now we can finally grasp strawberries and raspberries because we design compliant soft actuators. No, you don't need them. You can just do it with conventional mechanisms, and you're better off because this hand can do anything, and the soft gripper can only grasp raspberries, because otherwise it's too floppy to do anything. So that's that. So there's a picture which we have in this patent. And so the idea is if I run into something hard, then a conventional gripper would just stop because it couldn't keep moving. But this will just move the other finger in a little more until it provides enough force onto the object to take it with it. Now, the tactile sensor is still a success. People use it in Japan, and more importantly, Jacob Siegel and Richard Weir, who are, Jacob is actually a courtesy faculty in our department, and Richard is in Anschutz, and they do a lot of work on prosthetics. And there it's very interesting because you don't have a camera, but prosthetic people cannot feel anything. So what we've done is we took this sensor, and it has these nice properties that it can detect contact, and then you see as you increase the force, you finally touch something. But not only that, it uses multiple different sensors together, and there's some machine learning. I don't want to talk about it much, just so you see when you set out somewhere and you want to solve some industrial problem, nobody cares, but then you find a different application, which actually is quite successful right now. So with this hand that we built, we could do a lot of really cool stuff. And this is the canvas card that is a spin-off from our students a couple of years ago. And they gave us one to play with, and we mounted an arm. And so you saw this was what I had, the Lego figurine somebody made for me, which is this thing. And it can now go and pick out screws from these containers. And in robotics, you see a lot of one-off things where it only works once, but then never again. So what we tried in this video is to show that it can do this 3 times in a row. And it, of course, knows the approximate location of these things, but the card has maybe 10 centimeter accuracy. So it has to find the bins, and then it has to look inside the bins, and then it has to think about how to grasp them out. And interestingly, nobody wants to buy such a thing. It looks like something that I, as a computer nerd, thinks it sells like sliced bread, but no, I can assure you there's very little commercial interest into this. And I know, I mean, it's complicated. We can talk about it, but now other companies, actually Amazon just shut down. They bought it for a few $100 million, and then they just shut it down, this whole canvas thing. So different story. But so now this thing goes on and drives somewhere else in this. This was our company. It's actually Mod Robotics. It's this company in Boulder that makes the cubelets. So this guy is working on cubelets. And it navigates through this, and it can then go and do its trick a 4th time. And we don't have to film this 1,000 times like these basketball people who throw something into a hoop over their head on YouTube. We only had to film it 2 or 3 times. So I think it now delivers the bin. Okay, so I have another video to show off what this can do. And so just so you see where we are at with manipulation, and I do think these are still groundbreaking, or they have been groundbreaking at the time because nobody really did that. And I was able then to present all of this at a robotics conference in a longer talk because people took notice of it, even though we didn't publish any of this. And here it puts in grocery, and I've been working so hard on the grocery people. Hey, don't you want robots? Stock your shelves, unstock them. No, nobody cares. People are very good at this, and it takes forever. And so this is partly scripted, partly not. The idea is really to find these bottles using, at the time, use sift features. And now it actually unstocks the old ones, so it can put in the new ones to the back, and the old ones are still in front. So which we said is a great business case, but no. So this is neat, and it actually looks also where it has to put it every time. So it's not just scripted. And again, the card cannot move more than like, this is actually a Mir card, which you can buy commercially. and it cannot move more accurate than 10 centimeters. So when it arrives at this shelf, it has to look and use sensors and everything to do that. And then it uses these once it knows where to do it, it can do these pre-rehearsed behaviors. So this is also a neat trick that Austin came up with, who designed the hand so it can like flip around on these bottles. And that works very reliable. But again, it didn't happen. So now how does this work? What we came up with is really to use this 3D camera inside the hand. And the revolution at the time was that you can see up to 11 centimeters. So the Kinect can only see 50 centimeters. So this now can see very close, there's a dead zone. Then you get the point cloud. So you see these points of these things. And then you can try to find the plane or whatever the things are sitting on, or the bin. And then you can use TV scan or an algorithm of that nature to segment those pixels together. And once you have those groups, you can do principal component analysis, which sounds complicated, but it's not, to get these principal axes. And once you've done that, you can see which one of those are colliding. And you can't see that here on the screen, but basically I have multiple tries and I look which one can I do. And once I've done this, I can do the grasping. And so instead of publishing this, we just put it into the textbook. So now people think it's the way to do things. I think Aaron mentioned recently, it doesn't matter who invents something, it's what the community thinks, who did it. And so there's an opportunity for us to send that work home and basically, put a date on it. So I have one more video, but now I want to point out something else. This is bin picking. And it works very well, but in the second half of the video, you see some failure modes. And now then I'm getting to the technical part of the talk of what we are currently working on. So I think no failures here. Yeah, no failures. So wait until it do this one. Next one will fail. Oh yeah, these were two videos I cut together, and I think I cut failures in, yeah. You still cannot sell it, no, don't get me wrong. Okay, so here you saw it grasped right in the plane air because the camera has thought that there's something, but there wasn't anything. And maybe it's the wrong video. Oh, here. So here it slips. And these are very hard to grasp because they're from plastic, they're very slippery. So you saw it didn't work. So what does it do? It tries it again, and then it works. And so there's this whole notion in robotics that in computer science, you run the code, it works or doesn't. In robotics, you must actually deal with things not working at first. And then maybe you try it, and people would then say, well, it did work. It grasped the apple. And maybe they don't even notice whether it did work or not. So what I want to point out here is that when you do this manipulation task and you just saw it grasping like this, it is actually a lot of code and a lot of states. And so in this case, I go to this cube, then I align myself with it because this gripper actually is an all gripper which has to move together. Then I grasp it, then I lift, then there's maybe disturbance, and then I have a place event. And so if something here doesn't work, so this is the first code you would write, like state 1, state 2, state 3, but then maybe you didn't align correctly, so you have to go back. Maybe you didn't grasp it correctly, it doesn't load, so you have to do it again. So what you have to do is you add if statements. And when we went to these competitions, we would add if statements till the last minute, then we would go into the airplane, we would arrive to the conference site, and then we would add more if statements because something else would happen that we wouldn't, foresee. And it's really brutal. And so what we then discovered is something from the gaming industry, which now takes a foothold in robotics, which is called behavior trees. And behavior trees augments finite state machines by different, blocks. And so in this case, this is a sequence node. And what it does, it executes all its leaf in sequence. And there's a mechanism to provide ticks, they call it. And whenever you get a tick, it looks in the tree which graph is currently active. And so this is a selection node, which will do all of its leaves until one of them succeeds. And so in this case, it will run a state called ball near ? If that succeeds, the selector is done, and it goes on with the sequence to get the ball. If it doesn't succeed, the next tick will bring it here and approach the ball. And so then it approaches the ball, and it can go get ball. And again, does it have the ball? Yes, no, otherwise grasp the ball. And so this is very nice. When you go and take the ball out of the hand, it will actually realize this and go back and do it again. So in short, you save a lot of if statements, but it's also very modular and composable. Now, what you can do with this is you can create very complex motions, sequences, and this is a whole assembly sequence, and this is what my talk will be about. And Ken had to leave early. He hasn't made a decision, yes, on the content-based, So what this is one of these competitions. This is from NIST. They provide the sport, and then you have to show up somewhere and do that. And for some reason, this works much better here than elsewhere. And James Watson has taken this over as my PhD student. And last time we were in Macau, and we did that, and then we switched it to behavior trees. And this goes on forever. Maybe this is actually, I'm not sure, it's maybe 2 times real speed. And what it does is this very series of peg and hole assembly tasks. And this is a little more complicated. Again, it's a rehearsed, it's pre-programmed in a way, but it's also not, because it looks where the pulleys are, and then it uses force control to, and I will explain how that works in a second. And so this goes on and on and on. But the key here is it is executing a large sequence of autonomous behaviors that are sensor-based, and will fail, and the robot will retry. You don't see it. It will like wiggle and do things like that. So do we want to watch this whole video? Probably not. I think the highlight was the pulley. So the way this works, and James has published a journal paper on this peg and hole assembly, is you have to have some kind of torque force sensor that measures the torque and the force you exert at the wrist. And then you can do things like not just position control, but you can say, move down until you touch something, like a screw has to go into the hole. And then you can execute some kind of spiral search pattern. We have different search patterns, doesn't matter for now. And observe these patterns of your torque and force. And then you will realize when it slips into the hole, and then you can push it down. And so what this is very tight assembly tasks, which are also difficult when you do it yourself. Like when you're a human and you go into the lab and James has that stuff, you take the pulley that he wants to insert, it's actually difficult to do. So the question is, and this is the main point of the talk today, is can we speed up the assembly by detecting failures early? And so the way this would look like is I try, and then I fail, somehow there's a timeout, and then I try again, and I try again, and finally I succeed. So very typical what robots would do. But now if I can detect the error early, I could say, oh, this will be a failure. So I stop it and start over a little earlier. So I do that, and with this, my things shrink, and at the end, I save some time. That is the idea. And so this took us very long. Now, the idea is to combine this with this behavior tree framework, because the behavior tree, by definition, must know when it's done with very high or with very low uncertainty, because otherwise the behavior tree wouldn't work. And now the idea is I have this behavior tree for my twist insertion, but now I could have a classifier, and this is a parallel node. So this means all of these things are done in parallel. So all of this code is run in parallel, and it always does something in this bigger tree. And what it does in parallel is it records the false talk data, and then it runs this classifier that I want to have, which helps me to say whether something will fail or not. So this is how a failure looks like. Can you tell from this? No, but maybe machine learning can, and it does. But just so you know, because I never showed you, this is the kind of data. So this is the Z direction. So it goes up and down, and the other things are not so interesting. And then you see some peaks here talk about the x-axis is raising. And so I'm telling you this is a failure. Why? Because it failed. So that's how I know that this is a failure. I cannot tell from. And so what we've done is we thought a lot about how to classify this. And we used recurrent neural networks, and we used all sorts of stuff, LSTMs, and we realized the best thing is something called a dilated fully convolutional network. And what that is when it's dilated, it is when it skips input in the data. So it skips some pixels in an image, or it skips some time in this kind of temporal time data. And fully convolutional means that it only convolves. And so the output you get is then a 1/2, which is yes or no. And so the way this works is there's a window, and we took this method from these people that came out 2 years ago, basically unchanged, after trying many different papers and doing that. So the experimental setup is we have a robot that has to assemble this bearing, and it uses the smart hand that you've seen, which has a computer built in, and it uses the force torque sensor. Then the data comes in, it makes its decisions, but now it also sends the force torque data to another computer, which classifies it and tells the hand that whether it will work or not. So we now trained this network, and what we've done is we assembled this 250 times, and we disturbed it a little bit because otherwise it fails only like 1% of the time. Then we have only 2 or 3 samples. So we had to add some noise, so position error, actually only 1 millimeter, the standard deviation of the Gaussian distribution. And so with that, it failed half of the time. And now I have enough samples to train my detector. So the way this works is the detector waits for 7 seconds for the window to fill, and then it starts saying whether it's going to be success or failure. And what we do now is we have a threshold at 90%, and only if it reaches that, we decide and make the call. And so this one here is a true negative. It's very clear that it's failing from the beginning on. So there's a 70% of making it, but then it drops off really quickly. Later it thinks again it might be a success, but we know it's not. And then there's a false positive where for some bad reason it thought that there's a 90% success rate in the beginning. And that is where we would say, yes, this is going to succeed, so we're going to do this. So we have now something like a confusion matrix where we have the outcome is, does it work, positive, or does it not work, negative? And then we have whether the detector is true or the detector is false. And so we get true positives with 90%, true negatives 74%, and then we have also false positives, and even worse, we have false negatives. So 26% of the time, that thing says it will fail, but it actually will not fail. So we then stop it. So do you think this is good enough to actually make it preempt? I mean, is this good enough to make the policy work? A detector like this? Would you use that to say, okay, this is good enough for me. Whenever it tells me to stop, I will stop, even though you don't like it. So we didn't know either. I mean, we weren't sure, we have to try it. And so we did try it, and it's very messy data. This is 240 experiments, so 120 where we just do it the old way, and we just let it fail with a timeout. And then 120 times we do it with this monitor thing. And what you see is that there is a longer tail with unmonitored. So sometimes you fail really badly. It works, the ones that work quickly work faster. But then you also see here the monitored thing is actually better than the unmonitored. And now our Makespan is not 100 seconds anymore, but it's 83 seconds. So it did work. And now the question is, of course, that's not very interesting, because I really need to tell people, well, how good does the detector have to be so that you can actually use this? So the problem is, of course, the false negative, and many of you might have seen, I already wrote here true, negative, true, negative, true, negative, like these, but here I have a false negative that I shouldn't have stopped, because this would have been a winner. So I lost all this time, and so what I claimed here is I will save time. In the worst case, the policies will be the same. So you don't really lose anything, but it's still, well, they could even be worse. They could be worse, and I have the answers for this, but so the way we did it is we said, okay, this is a Markov decision process where I start, and then once I start running, nature takes its course, and I have a failure or I have a success. And now the rewards are the mean time to success. How long does it take on average to do this insertion? And how long does it take on average until I fail? And so now I have a Markov decision process where there's no decisions because there's only one policy here, which is whenever I fail, I'll go abort and start over and try it again. So that's all I can do. So now, but I do that so you see the structure of it. You see how the rewards work, how the probabilities work, and all of this. This is the MDP for the trial and error task. And now when I run, at some point the detector tells me success or negative. And if I do that, I have many options. I can have a negative, and this is a true negative. So I go to failure, and I have my rewards, and then I go back. But I could also have a false negative. And I also could not classify it at all, because the classifier sometimes in 8% of the cases doesn't do anything. It just, it's done before the classifier has made its call. So I have all these different states, and now I have numbers for all of these, because these are all my experimental numbers that I know. I can measure, yeah?
Does your MDP actually track how long a task has been running, or is it just all you know is that the task is running?
I know it's running, and I assume that it runs with these average numbers, which is the mean time to success. And you saw if you think about this picture, the time length, and I have these data. And so you can now solve this with value iteration or something to give you the policy. But we did something else. We modeled this as a Markov jump process, where you say, I have these states, and I start with running, and now I can either fail or I can succeed. And when I fail, I stay in the failure state on average MTF time. And if I succeed, I am stuck here on average MTS. And so you see now this does the same thing. I can fail many times until I finally succeed. And now I can also take this Markov model for the monitored policy. I hope you appreciate. I have the simple picture. This is really, you can like stare at it forever. It doesn't matter. The key is I have the false negatives, the true negatives, the false positives, and the true positives. And I think it's a very canonical model now, because a lot of tasks in robotics have that property that you have to try and try again. Now, I can solve this, and actually James figured this out. I didn't know you can do that. I would have needed that in my PhD thesis, but I actually used discrete time Markov chains, which have no tools to them. So this is a great tool, so I teach you if you are interested. The way this works is you write down the Markov chain in canonical form, and it's a matrix of transition probabilities. And so there's 7 states, so it's a 7 by 7 matrix, and you have probabilities for each of these states to switch. You can read them off here. But the idea with the canonical form is that you write the transient states into the top left, and this one absorbing state, in this case, is only one, into the bottom right. And you can easily do that because you know what that is. And then you can derive what is called the fundamental matrix of that Markov chain. And this is the equation. It involves a matrix inversion, and it takes the the absorbing states minus these states here, and then it inverts it. No, sorry, this is the identity. This is a little confusing. But so the bottom line is the fundamental matrix has at its entries the number of times every state will have been or is expected to be visited. And so once I have that, I can say, well, if I have the expected number of times the chain is in a certain state, you can sum up the rows of the fundamental matrix and get the expected runtime of the absorbing state. So now if you write all of these equations down, you will see that they're all pretty simple, and you can actually solve it analytically in Mathematica, and you get this equation. And this is very beautiful because you might, this is false positive and not classified and mean time to success. So these are all these quantities that I know, including my false positive and my false negative rate. And now I can compute the Makespan, which is the reward of that MDP with an equation. And that is cool because now I can make a decision whether I should do that or not by just measuring what I'm currently doing. So when you plot this equation, so this is this equation, and I plot it by sweeping, let's say, the failure rate, you can then see how much time would I save, like when I compared unmonitored and monitored. And so if I have 0 failures, then I don't save any time. And the more failure rate I have, the worse the robot performs, the more I benefit from this policy. And now, because I've already done the experiment, I can also plot what it is that we have done. So this failure rate was around 0.5, and I can see what the policies would do. So the equation predicts very much, it's actually a 3% error of what the experiment does. So you can do this for other quantities like the true positive rate and the true negative rate. And as the true negative rate goes up, you save more because true negative is good. It's the opposite of false negative. So more false negative means you wouldn't save time. And again, I just want to show that this works and the equation works and the experiments work. So this is another one, mean time to failure. When it goes up, the longer it takes until I fail, the more I benefit from preempting it. And this is the mean time to negative, which is the time it takes the predictor to actually say something on average. So I think there are many trial and error tasks in robotics where you have that. And for instance, opening a drawer is something like this. You go to the drawer, it doesn't work, so you work it until it opens. A robot has to do the same thing. In that case, it's maybe the kinematics of the robots that are wrong, so then it has to move its body, so that tries again. Parallel parking is another thing. You don't do it much in this country, but when you do, then I see it sometimes on the street. So you try that and you say, oh, it doesn't work, so you try it again. And what you need to know is you have to have some prediction of whether it's going to fail or not. So again, if you had such a thing, inserting a screw into a screw is something like this. And then I think all this whole mobile manipulation in general, because there's so much uncertainty, and this is from the Intro to Robotics class final project, the students have to have this robot and have to grasp these cubes out of shelves, and they're yellow and simple and things, but still there's noise and problems. Now, I think the interesting thing is now that I have this framework, I can do that task, and I can have the robot in my house or the car, and I can actually train the failure detector. All I need is I have to have a very high, low, I always confuse, I have to have a very low uncertainty thing that tells me whether I made it or not. I just have to know the car has made it or the car has not made it, the drawer is open, the drawer is not open, and usually I can tell that with very low uncertainty. And so if I have that, then I can train this detector because all my trials will contribute to this. And I can now switch over, which we haven't really tested, once it's advantageous. And now what I'm interested in is, imagine you have a BT library and you just enable this feature that, because the BT by definition, it knows when it's done, and you just say, take all your sensor data and harvest it all the time to see, can you predict whether it failed or not? And then you can say, if it's 20% better or 30% better, then switch and actually use this. And you don't have to program this ever again because it could do it automatically. It's a future work, I haven't done it yet. So the other thing is, you have these tasks which are very well understood and very well known, like assembling some, peg in a hole. But you have, or parallel parking, all the things I mentioned, but you have this crazy environment around you. And I've been thinking, not doing, but just thinking it is discussion. There's an inverse problem, which is to not minimize the make span, so how long it is going to take, but what I want to maximize is whether I will actually succeed. So the parallel parking, I want to maximize the probability that I park the car. I'm given as much time as I want. And I think tasks like this are to serve a golf shot, where people would try and then they would abort. And I'm not really a golfer, and I don't even play tennis really anymore. But I know when I play, I try to throw it and then for a serve, and then I would abort, and I would then bounce it again, and then I would try again, and I say, oh no, it didn't work. So I think you have a failure predictor there, and I have two shots, and what I want to maximize is that I'm successful. So it's the inverse problem, maximize the K-shot success rate, something we can look at. But so right now, so James is paid on a project with somebody in evolutionary biology, Nicole Barger and Chris Heckman. And the goal is to do landscape revegetation. And so the way this works is you can go into a desert, and actually the majority of the planet has that problem. It's desertified, and also here in Utah and Colorado, and it got worse because of global warming. You can go and make divots into the whole surface, and that will capture the water, and there will be vegetation that takes a foothold, and from that the landscape can recover. And so what we have is a project where a robot should do that in Utah. And the way this works, so James and Kristen are currently there, and what they've done is they created a seed planting mechanism. This is something you can buy, and it has they bought a mechanism that will shove the seed in. And I think this is also a trial and error task, because you might hit a stone or something like this. We don't have force sensing yet, so this is a little premature to call it that. But the other thing that James came up with is to place so-called con mods. And this is an established technique. People do that already. They would place little meshes that look exactly like this. James built that himself. And you place them into the landscape, and the dust will collect there, and that's where vegetation will get a foothold and then reclaim that environment. And so what we want to do, because we're interested in peg and hole assembly, we're really only interested in peg and hole assembly, so all of this is peg and hole assembly. It is about shoving that con mod into the ground, and because it's too difficult with 4, James made it 4 pieces, and what you have to do is you have to assemble them, but now maybe the 4th one doesn't work, and so you have to go back and take the whole thing apart again and do the assembly then. And that's something I'm very interested in, because in assembly, maybe you do a mistake and you think it has a true positive, a false positive. It told you were all right, and then you fail much later, the robot has to shut down. Now instead you can say, hey, wait a minute, none of this might be true. What is the likelihood of me going backwards in time, undoing this, and then actually correcting that? So we want to do this, and it's very easy. We don't have to travel to Utah to try this, so we'll do that here. What we also do for this replanning, Dylan Kriegman is doing a senior thesis with me right now, and what we want to do is we want to revive strips a little bit, and it's actually not dead. There are many conferences on PDDL, and that field keeps pushing forward to expanding that logic and language-based reasoning. And so in this case, what Dylan is doing, he's assembling a tower of blocks, and this is a simulated environment, so you see the robot sees these things, but then tries to write down a PDDL description for the problem, and in this case, you see this action to move the blocks. So there's a precondition that the blocks have to be somewhere, and there's an effect that the blocks then are later somewhere else. And what we hope is to get this PDDL planner to work with a reasoning engine that reasons about the uncertainty of all of these things, and then says, okay, at this point, I believe the tower didn't fall, so I don't have to go back, or maybe I placed the block the wrong way, so I have to replan the whole thing. So ongoing work just started. What we also do with Steve is doing a master's thesis to make the hand that we have and that we sold for a couple of years, but then stopped selling it because not enough people want to buy it, too complicated, to make it an open source version. And the cool new thing is Intel shut down the RealSense project, only to revive it and coming out with a new RealSense, even smaller, which fits right here. And so now, instead of having $5,000 in parts, we have like a $300 gripper that we can hopefully put also on Alessandro's robot and Brad's robots, who has Canova and Sawyers, and Alessandro has Pandas. I have the Universal robot, and use all of these open source tools like Open3D that we use in the class, and all these algorithms for inverse kinematics that we developed here, and push them out for people to use. So I think to discuss this, the manipulation requires constant replanning due to failure. This is really what I learned. It's not just only to realize that you haven't made it, you have to actually reason about these things in a very involved manner, especially if you start considering false positives and false negatives. So the robot tells you I did it, but it didn't, or the robot tells you I failed, but it didn't. So even a simple thing like picking up a cube has already 8 different states. Doing an assembly like you've seen has thousands of states. It's very complicated to manage it. I think these false negatives and false positives will not go away, but they become more as soon as you venture into more interesting domains. And so I think you really have to do inference over all the possible states something can be in, and backtrack. All right, so that's it. I think I could demonstrate to you that picking and grasping and precisely applying forces to objects is really a solved task. What is not solved is the business case. And it's a very difficult, completely different conversation why people don't need that. I think manipulation is now really a probabilistic planning problem. It's very challenging, but you can do it on a tabletop, so I like it. I don't think replanning based on failures, like everyone else is doing, is sufficient. You really have to replan based on false positives and false negatives. And the edge cases are the new normal. Before, you had like a paper, they grasped something, and they ignored all the problems that happen only once in 100 times. If you have 1,000 states you have to go through, you will have 10 of these events. And so I think with that, that is my conclusion. These are all the people who work with me on manipulation, no professors, even though there are many, but I did only put the pictures of the students and the people who worked in the company. And many of them have now ventured onto greener pastures. Dylan and James and Stephen are currently with me. And with that, I'm happy to take questions. Sure. Oh.
All right, so I'll go first. So I think this is a very, the whole idea of Makespan is very interesting, but one suggestion I had was, often enough, if you're going to do a long task that takes 20 seconds, right, detecting a failure 1 second into the task versus detecting a failure, like possible failure, predicting a failure 19 seconds into the task, right? I think your policy will have to take that into account, right? So at some point, that's why I asked the question whether
it does.
discrete time or a continuous time FTP, right?
Yeah, I didn't explain it because it's too boring, I thought. But we not for you, I know. But we have the mean time to negative and the mean time to positive. And so the mean time to negative is the key number. How long does it take me on average until that thing? And if it never tells me, and so I also skipped that here because again, it gets into the bottom of it, and thank you for picking it up. So here's the mean time to negative. As the mean time to negative increases, as you predicted, the band policy will go, down. Is that answering the question?
Yeah.
Thank you. You had a question, yeah?
Just interested to know like how this failure prediction model of translate to some other things like so I feel like there's a lot of potential there that we can create.
Yeah, thank you. I try to, that's why I try to use it with BTs where you can see yourself easier in. And so if this is the parallel parking BT, I need something that runs in parallel and constantly soaks in all the data and says, this is going to fail, or this is not going to fail. So you have to cast that. I chose examples where I thought, I haven't done it, but I thought it might be actually doable by looking at certain like distances or what the person does at the steering wheel. You say, okay, failure, no, stop. And so I'm very interested in trying it out on different domains. So if you have one, I would be curious too.
So if I'm getting it right, so we have to reframe it in a way that it is compatible with tweaks.
No. It just has to run in parallel. I have to be able, there has to be information. There has to be some kind of information that correlates with the failure. And who would have thought that this correlates? But we thought it must. We actually claimed this in the first paper, and the reviewer said you can't just claim that. So we then removed that statement. But we said in the future we would like to. We think, we showed other pictures which were very clear. But you don't know. You have to try whether you can get that data. Brett?
So thanks for the talk. So for all these failure detections, I feel like there's this implicit assumption of like you're entering into a reversible failure, or that it's a good idea for the robot to try again. So in the parallel parking example, like I can imagine, say in the advanced robotics class, one of the challenges they have to do is implement a controller where the car parallel parks. And some of them solve this by having the car slam into one of the cars and like widen the parallel parking space. I can very easily see, one of these autonomous cars thinking like, well, I'm going to try again. Like I only hit them a little bit, right? So have you thought about failure type classification and how that plays into any of this?
No. So for your example, you have to detect it before you slide in and say, no, I abort this. But once you slide it in, you already succeeded. So I haven't thought about that. I realize I have a hard time. I'm still working on classifying what this is, and what I put out here is trial and error tasks, because I thought that captures it well, but that doesn't mean much. And so it's a good question. I think one has to narrow down what is the nature of a task of that nature, which we don't know. So, and I think maybe you have some ideas. I would be interested on how to classify these failures and say, because if you do contact-based manipulation, it's just like me shoving the peg down until I touch and then do spiral. That's fine. That's exactly your example. And that's part of my detection. Yeah, Noah?
I'm wondering, so if you detect a failure or think that a failure is going to happen, does it automatically go back to the initial state, or is there some state that it goes back to that's not the initial state, where the probability of failure is lower than it?
No, it restarts and it picks up, it replaces the peg and picks it up again. Thank you.
We have time for one more. Let you get his hand up.
I was ready to spend. Going back to that question about in the context of, let's say, self-driving car, I think what you can do is you can let the human driver try to park the car, but then on top of that, you can have a monitor that shields the car from the crash by doing some sort of like reachability analysis. And then every time the monitor switch from the human to the safety, so you can actually like tag that, and then that way you can prevent the crash that rather than talking about. So you can do that. It's possible to, in the context of not manipulation, which is not safety critical, you can always try, and even in the context of self-driving cars, that's a bit good.
Yeah, it's interesting to use, but I don't see if I have false negatives and false positives, and then the space is blocked in the reachability, then maybe. But I'm curious to hear your more detailed opinion on this. Yeah, I reached out before to hear what you think and how to get to this. And thanks, Majid.
A quick clarifying question for the behavior tree on the question mark selector. Is it better to just have a binary option, or can you have more than binary?
Yeah, you can have ball near, battery charge, whatever. So in this case, actually, it will stop once the first thing succeeds. So you have to sort them to what you want to get done first.
Is it better to have less or more options?
I don't know, it depends on, this can be very deep. So in computer games, these are thousands of nodes.
Thank you, Nikolaus, again.
Thank you all for coming.